Hello, everyone, and welcome to the Parsons Technical Webinar Series. I'll be your host, Jessica Bennett. Today we have with us Ted Schoenberg presenting on groundwater treatment plant retrofit using native iron for Fenton's treatment of 1,4-dioxane. We'll go through a few housekeeping items first. We will be keeping all phone lines muted until the end when we'll have a Q&A session. If you have questions during the webinar, you can submit them at any time using the chat feature, or you can wait until the end to ask either via chat, or you can raise your hand and ask it live. This webinar has been approved for 1 professional development hour or PDH credit. Ted, could you go back 1 slide, please? Thank you. If you'd like to receive that PDH credit, you will need to get the attendance form, and it will be posted in the chat a few times throughout the webinar. There are a couple of multiple choice questions you'll need to answer to get that credit, so please take a look at those, which we'll also post in the chat if you have any issues getting the form. If you have any problems getting this form or any questions, you can send an email to us at daniela.savin@parsons.com. And finally, this webinar is being recorded and will be posted on our YouTube channel in the coming days. So just a brief agenda for our overall webinar today. We'll introduce our guest speaker, Ted Schoenberg, first, followed by a core value moment. Then we'll get into the technical presentation, and we'll wrap up at the end with the Q&A session. So a little bit about Ted. He is a supervising process engineer and project manager at Parsons with over 23 years of experience. He manages the Parsons Treatability Lab in Syracuse, New York. And he has experience with planning, conducting bench and pilot scale treatability studies for a wide variety of treatment systems for industrial wastewater, remediation groundwater, construction water, leachate, and sediments. And he's also involved in process development for design, construction, and operation of full-scale treatment systems, as well as environmental compliance and permitting. And with that, I will hand it off to Ted for the core value moment.
Thanks, Jessica, and good afternoon or good morning, depending on where you are. I'm going to start off the presentation with a core value moment. Today, I'm going to talk about innovation. I'm going to focus my discussion of innovation on municipal wastewater treatment systems or publicly owned treatment works, although the principles certainly apply to industrial or private treatment systems, and I hope to demonstrate that today during my discussion of the main topic. I also hope to show how innovation dovetails with several other Parsons core values. So focusing the discussion here on POTWs, we're talking about treatment systems that are typically run by municipalities, cities, towns, treating residential wastewater, commercial wastewater, and oftentimes industrial wastewater. And for the latter case, the industry generating the wastewater may be subject to pretreatment limits under a sewer use ordinance, but generally just municipal treatment systems. The wastewater characteristics of municipal wastewater typically involve high organic strength, usually measured as chemical oxygen demand and biochemical oxygen demand. We're also looking at nutrients mainly in nitrogen and phosphorus based. And as I mentioned, there are potentially some industrial pollutants, although they typically may undergo some level of pretreatment. The treatment that goes on in municipal wastewater treatment plants, there may be a physical chemical process, for example, primary settling. If there has to be some metals removal, there could be an iron precipitation system, for example. But the centerpiece of a lot of municipal wastewater treatment systems would be an activated sludge process, which is an aerobic biological treatment process. Plants often do have to deal with nutrient removal, and then they do have to manage the solids that are generated typically from that conventional activated sludge process. And some of the points I got for my discussion of innovation today come out of the reference which I show on this slide. I just wanted to point out some of the challenges that drive the need for innovation. With municipal treatment systems in particular, you're typically talking about systems that more or less do the same thing, and so the people that plan these systems, they just need to depend on the old reliable technologies, and so they typically adopt a conservative approach and they may be a little reticent to look at innovation just culturally. But given the fact that there are drivers, there are changing conditions, this does drive the need for innovation. And some of these are listed here: the availability and quality of water resources, growing population, aging infrastructure, climate-related changes, changing workforce dynamics, and then emerging contaminants. And emerging contaminants is something I'm going to be talking about during the main topic of this webinar today. Some of the innovative developments in wastewater treatment are listed here: water reuse. And I should say that Parsons has been involved with significantly large water reuse projects. I believe there was one out in Los Angeles where water is a scarce resource. And so something like water reuse does provide substantial environmental and societal benefits. Some of the other innovations include energy recovery. For example, in sludge digestion systems, they implement systems where they recover methane, which they can use to heat the process and for other energy needs. Sometimes some of the additional innovations include means for reducing the amount of solids, because fewer solids means fewer truckloads that have to be trucked away are otherwise dealt with. And then there are cascading savings from that. And then there are innovative developments in nutrient removal and recovery. And I'm actually going to be talking just very briefly about that in this part of this discussion. And just some of the benefits of innovative developments include reduced costs, increased reliability in achieving treatment goals, which dovetails with our quality and safety core values, and then environmental benefits as well, which has a sustainability benefit to it. Just real quickly, and this is just a brief example of innovation in municipal wastewater treatment. It has to do with nutrient removal. Nitrogen typically comes in the form of urea or ammonia. Processes which deal with these include nitrification, which is also an aerobic biological treatment process. So if the system is already treating the wastewater biologically to knock down the organic content, you could just have the system also designed and operating to knock down ammonia using aerobic processes. And that, of course, means you have to supply oxygen. Nitrification is energy intensive. It does generate sludge because of the bacterial growth, and it consumes alkalinity, which means that you have to monitor your pH and replace caustic, for example, to maintain your pH. And so that would provide like a demand on chemical use, specifically something like sodium hydroxide. Denitrification is another process where you're actually, if you have a nitrate limit, nitrate is this NO3 minus. If you have a nitrate limit, you may be required to reduce that. And a typical way is through a process of denitrification, where you have bacteria degrading an organic source. Sometimes it has to be added, and this is done in the absence of oxygen, and that converts to nitrogen and the nitrate to nitrogen gas, which then just evolves to the atmosphere. One of the benefits is that you do recover some alkalinity, and sometimes that can drive inclusion of a denitrification process in your treatment system. So real quick, just I've been hinting on or demonstrating that nitrification in particular is an aerobic process. Aerobic treatment can or just energy in general from municipal treatment can consume up to a third of a municipality's total energy bill. So that's just for that wastewater treatment plant down the road, may use up to a third of the entire town's energy that they use for just their all their needs. And the energy that's used for the aeration process within that treatment system is it's about 40 to 70%. It may be towards the higher end of that range when you have the nitrification. And so just one innovative process that I found in that reference I mentioned earlier is something called anaerobic ammonia oxidation, or ANAMOX. So as I had showed before, the nitrification process, the energy and intensive process to provide oxygen It converts ammonia to nitrite and then into nitrate. And what this anammox process is able to do is take a slipstream of this water with the intermediate nitrite, and it's able to apply this directly to the ammonia. So instead of requiring the oxygen to oxidize the ammonia, you're using the nitrite, and what that does is it actually converts the ammonia directly to nitrogen gas. So it's just an example of an innovative process with nutrient removal on a municipal treatment system. And just based on that reference I had showed, the example, it was in Alexandria, Virginia. They were able to lower their costs for dealing with nitrogen from 266 per pound of nitrogen down to 93 cents. So that's a significant cost savings, and it's a significant reduction in energy use. So now on to the main topic today, where I'm going to be talking about the retrofit of an existing groundwater treatment plant using native iron to address 1,4-dioxane. I'll just briefly introduce the treatment system. I'll talk about the investigation which led to the selection of an alternative to explore for treating 1,4-dioxane within the existing treatment plant. I'll talk about how this was implemented at full scale and how we demonstrated it during startup and operation, and then we'll end with a Q&A session. So just a brief introduction. The groundwater treatment plant is located in New Jersey. It was not designed by Parsons. It was designed by not a predecessor for Parsons. It was designed by the previous client's primary consulting firm. Then Parsons was awarded the contract with the client and took on managing the construction of the treatment plant in 2010. The plant construction was finished in 2011, and then Parsons was tasked with starting the plant up, which we did in late 2011 and into 2012. The plant was implemented to provide hydraulic containment at the client's site. It's an active site. They produce. It's a global manufacturing / chemical production site. The groundwater treatment includes the extraction of groundwater from 6 extraction wells, and then the treatment of target constituents to New Jersey groundwater discharge standards. And I'll get a little bit more into the details coming up. The flow capabilities, the plant is designed to treat around 400 gallons per minute with a peak of 500. The plant typically operates at 300 on any given day, depending on the number of extraction wells that are online. The target constituents for which the plant was designed for include nuisance and target metals. So this includes iron. I'll show you that they do have a fairly large iron load from the groundwater. They also are beholden to treat aluminum, manganese, and arsenic. They treat vinyl chloride, and they treat perfluorooctanoic acid, or PFOA. So I show a block flow diagram of how the treatment system operates. The flow from the extraction well, the pH is raised, and it's also aerated, and this is to oxidize the iron to allow it to precipitate. This water with the precipitated iron then goes, or the oxidized iron, I should say, goes into a chemical mix flock process, and then a plate settler where the pH is further raised to make sure the iron is completely precipitated. Then you hit it with a polymer to agglomerate those precipitated solids, and then allow them to settle. The solids are managed through just the sludge underflow is pumped to residual settling basins, and then they're managed further from there. I won't get too much into that beyond for the rest of this presentation, but just wanted to point that out. The treated water proceeds through this. Now, this is how it was formerly designed and operating up till the current requirement for treating 1,4-dioxane. So this is the previous block flow diagram. The water was filtered through continuously backwashing sand filters. Then the water from that point proceeded to an air stripper to remove vinyl chloride and other VOCs. The water then proceeded through GAC adsorption to remove PFOA and then other VOCs, which would be removed by it. And then the water was discharged to a series of rapid infiltration basins. So as I mentioned, the treatment plant was designed, and built in 2010, 2011. Around 2015, New Jersey established an interim groundwater quality criterion of 0.4 micrograms per liter for 1,4-dioxane. Now, we talk a lot about units and concentrations for emerging contaminants, and they tend to be very low. 0.4 micrograms per liter is also approximately 0.4 parts per billion or 400 parts per trillion. So one way to visualize that is if you think of a cubic centimeter as being 1 milliliter, it would be that volume or that size in a box 10 meters on a side. So that's what 1 part per billion would be. And the standard is now 0.4 parts per billion. 1,4-dioxane properties. This is just the structure of the molecule. It's nonpolar. It's miscible, so it's completely, soluble in water. It also has low volatility. The treatment plant was not designed specifically for 1,4-dioxane. And as it turns out, the unit processes that do exist would not really lend themselves to treating it. And I'll get to that in a moment. Excuse me. So now let's talk about the investigation which led to the alternative that was selected for treating 1,4-dioxane. The first step was to characterize to see if, in fact, 1,4-dioxane was of concern. And so there was a focused sampling effort at the extraction wells. And as you can see in this yellow highlighted row for 1,4-dioxane, the concentration in most of the wells did exceed that interim criterion by quite a bit, actually. The weighted flow weighted average for the influent was around 7 micrograms per liter. So they definitely were going to have to address 1,4-dioxane treatment within the treatment plant. A couple other things to note in this table is you can see that there are the iron concentrations are pretty notable. Average total being about 50 milligrams per liter, and most of which of that was soluble. And typically, when you're extracting the groundwater, if you have soluble iron, it's usually in the ferrous form, or it's a valence state of +2. So that's actually less oxidized than ferric, which is Fe +3. And then just a couple. One more thing I do want to mention is that we also measured bromide, and I'll get to that in a moment, why that's important. So we basically did a tabletop exercise to consider different technologies which may address 1,4-dioxane. So some of the conventional treatment processes which we considered included air stripping, because there was already an air stripper there, but because of the low volatility of 1,4-dioxane, that wasn't going to be an option. 1,4-dioxane is somewhat sorbable to GAC, but not nearly enough so that you could use that as a reliable treatment system, process. Even though the system already has GAC, that wasn't going to be a reliable means. We were able to do some projections which would show that 1,4-dioxane would have broken through within a week or two of replenishing the carbon, and so that wasn't an option. Biological treatment is a demonstrated means in certain situations for treating 1,4-dioxane. Parsons actually operates a treatment plant out in Denver, Colorado, where biological treatment is used to treat 1,4-dioxane. But it just so happens that in that particular location, there's a co-metabolite present. I think it's tetrahydrofuran, which allows the 1,4-dioxane to be treated co-metabolically. That certainly wouldn't be the case in our location here. And also probably more importantly is that biological treatment would probably be a bit more complicated than necessary, especially when we're trying to wedge it into the existing treatment plant. So we also looked at a number of advanced oxidation processes. These are widely applied for 1,4-dioxane treatment. These include ozone peroxide, but we decided against that due mainly to the it is energy intensive and it does pose a potential bromate formation potential that is due to the presence of bromide, as I had shown you on the during the well investigations. We also looked at UV peroxide and did take that into consideration. It's a little bit less energy intensive and simpler than ozone. Of course, you have to add peroxide as a new chemical, and there is also the potential for bromate formation there. Fentons was considered mainly because of the ready supply of ferrous iron in the background. Of course, when you add Fentons is performed at a lower pH, and so there would have to be a means to reduce pH, meaning we would have to be adding acid, so we'd have to have acid storage and metering and peroxide. Just a brief summary of what we're talking about with advanced oxidation processes. We have hydrogen peroxide, H2O2, coupled with either ozone, UV, or ferrous iron, forming hydroxyl radicals, these little things here. And these are highly oxidative, and when they're generated and released into a water stream that has organic constituents, the hydroxyl radicals will attack those organic constituents. The Fenton's reaction in particular, it's typically conducted at pH 3 to 5, hence the need to add sulfuric acid at the front end of the treatment process. Ferrous iron, this is the Fe plus 2 plus the peroxide, generates the hydroxyl radical, and in so doing, it oxidizes the iron to Fe plus 3. And so you have that benefit of, instead of having to aerate the water, you now have hydrogen peroxide doing it for you. So you're getting a secondary benefit, or actually, it basically kills two birds with one stone. You're getting the Fentons to occur, generating the hydroxyl radicals, but you're also getting the iron to precipitate, which is what you need to do anyways to remove it. And then this the iron then is coupled, or when it reacts with peroxide, you regenerate a ferrous iron and you get what's called a super hydroxyl radical, and that provides additional oxidative capacity for going after the organic pollutants you're trying to treat. I mentioned this potential for bromate formation due to the presence of the hydroxyl radicals. There's a whole series of transformations which I decided not to show. I just wanted to, I thought it would suffice just to mention that bromate does form in these types of systems depending on, well, it's really site specific. Now, why is bromate a concern? Well, it is a suspected carcinogen, and there is a federal maximum contaminant level of 10 micrograms per liter. This has come up on previous projects in which Parsons was associated with, specifically for 1,4-dioxane. There was a treatment plant out in Arizona where the treatment plant already had ozone peroxide installed, and we were tasked with optimizing that process to reduce bromate, because bromate was on occasion pushing that 10 microgram per liter MCL. So based on that experience, we were on the lookout for it potentially forming here. So now that we selected our two candidate advanced oxidation treatment processes, we proceeded to bench scale treatability testing to validate the concept for our specific wastewater matrix. Bench scale testing was performed in 2 phases. In the first phase, we did range finding tests. So we took our treatment testing roadshow down to the site and performed Fenton's reaction testing. We also had a UV peroxide vendor do some testing for the UV peroxide treatment process. Phase 2 refinement, spoiler alert, we didn't go with UV peroxide, so we did refinement testing with Fenton's. Again, this was performed on site. The test water, as I was saying, we were using the actual water that they're treating down at the New Jersey treatment plant. We would use freshly collected water because we want to have it reflect its initial background conditions as closely as possible, specifically the state of the iron in that water. We did spike the water with 1,4-dioxane just to provide us with a larger concentration which we could compare or evaluate treatment. This is just a result from a summary of the results from our phase 1 bench scale Fenton's testing. Just go through each of these columns. In the leftmost column, we're showing the peroxide dose in milligrams per liter, and we went kind of high for the initial demonstration. We tested within this range. We tested pH at 3 without supplemental iron, and then we did some tests where we did add supplemental iron just to see if it made a difference. And then we repeated these tests at a higher pH 5, with the same 2 scenarios where in some of the tests we just relied on the background iron, and then in some tests we added supplemental ferrous iron. Results are summarized over here. We were looking at 1,4-dioxane, the spiked concentration being around 60 or so micrograms per liter. At these relatively high peroxide doses, we were able to treat them down to non-detect when we did our tests at pH 3, whether or not we added supplemental iron. So that was a good initial sign. The tests we ran at pH 5, that higher pH, we actually did have detectable dioxane concentrations that were above that interim criterion of 0.4 micrograms per liter when we ran them at pH 5 without supplemental iron. Although when we added supplemental iron, we were able to show it was non-detect. We also measured vinyl chloride because that's a target constituent and it's an organic. And so we figured, well, maybe that also gets taken care of with the Fenton's. And sure enough, we were able to demonstrate that at all our test conditions in our bench scale, our range finding tests, that we were able to achieve non-detect. We also looked at bromate. Bromate was not detect in any of our tests. So that was a good initial sign for Fenton's. The total iron, we were right around 50 or so milligrams per liter in the influent, and that actually was, most of it was oxidized, precipitated, settled out, and was removed in the process of, number one, taking part in the Fenton's, and then just being, being removed because it had precipitated and flocculated. We also looked at PFOA just to see if this advanced oxidation process would work against that. No change in the concentration. Also, during phase 1, as I mentioned, we had a vendor do some UV peroxide testing. So they tested a range of intensities here shown in millijoule per centimeter squared up to 4,000. The peroxide dose in these tests, I believe, was 15 milligrams per liter. That was just based on discussions with a vendor that would be the appropriate dose for this type of test. Under those conditions, the influent dioxane here, again, had been spiked into the water, was around 52 micrograms per liter. The water we sent to them for these tests, we had already removed the iron so that we weren't sending them a bunch of, iron-laden water that would all come out of solution. So basically, the concept would be that if there was UV peroxide, it would be applied after the chemical precipitation and settling process. So we sent water that would be representative of that point of the treatment system. Even at the highest UV intensity tested, they still had a dioxane concentration of 1.4 micrograms per liter. Now, granted, our influent likely wouldn't be at 52 micrograms per liter, but even if you scaled this to the quote unquote worst case scenario, there was a possibility that on occasion we would be above the 0.4 microgram per liter criterion. Vinyl chloride was reduced to non-detect in their tests. There was some bromate formation at the higher dose. It didn't push that 10 microgram per liter MCL, but the fact that it did form and it was, a pretty decent percentage of that MCL, was also a reason for pause. So for phase 2, we proceeded with Fenton's testing alone. In these refined tests, we number one looked at lower peroxide doses. We also took reaction time, as an important variable, because that would essentially, reaction time would translate into the size of a reaction vessel that you would ultimately need. And so we wanted to capture that in our bench scale testing, because then that would help us design a pilot system, a pilot test. So in all our tests, we ran these at, I don't show it here, but I believe we ran all these at pH 3, because those were the tests in our phase 1 tests where we did not have to add any supplemental iron. So we kept our testing at pH 3 for this test, relying just only on the background iron. In all our tests, again, we spiked 1,4-dioxane. We had an influent concentration of about 34. It was non-detect in all the tests we ran. So at the lowest dose, regardless of the reaction time. And again, we showed vinyl chloride was reduced to non-detect. So the summary here is that we treated both 1,4-dioxane and vinyl chloride to below detection at the lowest test dose and reaction time. So now we're moving on to pilot scale testing. So we wanted to demonstrate this process operationally. We consulted with the operators who are Parsons employees that work with our group down at the treatment plant in New Jersey to build and operate a pilot test. So here's a picture of the test. The unit processes or the sub processes, I guess you could say, for this included a pH adjustment tank. So that's the first tank over here, where sulfuric acid was added to reduce the pH down to around a target of 3. Then in the second tank or vessel here, peroxide was added to affect the Fenton's reaction. And then in the third tank, we had a pH readjustment step. And this is also where a lot of the iron came out and settled out. The test variables for our pilot test included peroxide dose. So since we had demonstrated effective treatment during the second phase of bench testing at 50, we decided to go even lower. We had the opportunity to try several different scenarios. We also were able to show a range of reaction times. Here again, we showed that 15 minutes had worked, and so we did some tests where we reduced that reaction time down to even 5 minutes. And we also did test a range of pHs. So even though our initial test had implied that you might not have enough background iron at pH 5, we decided to test it anyways, just to see if there was anything that happened during pilot testing that would show that we could maybe run it at a higher pH. This is just a light piping and instrumentation diagram of the treatment system I just showed. As I showed, there were 3 tanks, a pH adjustment tank where 25% sulfuric was added, a second tank, a Fenton's reaction tank where 30% peroxide was added, and then a pH readjustment tank where 25% sodium hydroxide was added. Here's a matrix of the tests that were run down at this. Here again, this is all down at the site. Now, in these tests, We did not add supplemental 1,4-dioxane. We just relied on the water as it came in from the extraction wells. So I highlighted in yellow where we departed from that refined bench scale, the refined bench scale testing conditions. So our base case was that the lowest dose and HRT that we had demonstrated during bench testing at pH 3. And in that case, we were able to show reduction down to non-detect. From now, the influents were a lot lower. They were even lower than what that average influent concentration would have implied, but they were still high enough to demonstrate treatment. They were still well above that interim criterion of 0.4 microgram per liter. So in that case, in our first test, we showed non-detect, and then again with vinyl chloride, which we're also monitoring, that went non-detect. Lowering the peroxide dose while keeping the hydraulic residence time the same. Same story for 1,4-dioxane. It went down from around 1 or so microgram per liter down to non-detect, and vinyl chloride, which we measured in some of these tests, went down to non-detect as well. So then we went back up to our base peroxide dose and looked at a lower residence time, so which means the smaller amount of time for the reaction to occur in that Fenton's tank. Again, non-detect across the board. And then finally, we did one test where we ran the base peroxide and HRT conditions, but at a higher pH of 5 this time, and again, non-detect for 1,4-dioxane and vinyl chloride. So based on the results from pilot testing, the plant was retrofit with a Fenton's treatment process. So this, so now we have a revised list of target constituents where we've added 1,4-dioxane. And so just in comparison to what I had shown before with a block flow diagram, in the former treatment process included a cascade aerator at the head of the treatment process. That was taken away, and in its place were added 2 tanks in series. In the first tank, we had pH adjustment where we had sulfuric acid. The second tank is a Fenton reaction tank where peroxide's added. This water then flows to the plate settler, precipitated oxidized iron and all. At the plate settler, the pH is readjusted with sodium hydroxide so that the oxidized iron can precipitate. Once the iron is precipitated, in the next chamber, it's hit with polymer, just like before, where the precipitated iron then agglomerates into settlable flocks. So that's the same as before. The retrofitted groundwater treatment plant retained the continuous backwash filters, but those are actually offline as of now. So you can always put an extra that filtration step as well. And then we're now bypassing the air stripper because in our previous tests, the pilot tests showed that the vinyl chloride was completely eliminated due to the Fenton's reaction. So no need to go through the air stripper anymore. Then the water proceeds through GAC absorption, where now it's really focused primarily just on PFOA and then discharge to the rapid infiltration basin. Just wanted to mention that the peroxide concentration, the solution used for full-scale implementation is 30%. Just some pictures from the retrofitted groundwater treatment plant. The one on the right best shows the Fenton's treatment process, the newly built tanks. These had not been here before. Before there was a cascade aerator that was up on a platform, so that was taken out, and in its place was put this bermed or this concrete walled area housing, and providing secondary containment for the pH adjustment tank as the first tank, and then behind it, based on our perspective here, the Fenton's reaction tank. Just another perspective. So going right to left being the pH adjustment and the Fenton's, And then in the picture on the right here shows the new chemical storage and metering that was built. So initially the plant had storage and metering and secondary containment for sodium hydroxide. So now the chemical storage area includes dedicated walled areas for both the sulfuric acid and the hydrogen peroxide. And then there's the controllers in these boxes for the pumps so that you can add those chemicals at the points where they need to be added. So now I'm going to talk about startup and operation. The treatment plant was down, I believe, during the entire phase of the entire construction phase, while the Fenton's process was being installed. So this took place in, I believe, the spring and summer into the early fall of 2023. So once that was completed and all the commissioning was completed, we went to the startup phase where the plant was restarted, and this included now the Fenton's process. The startup test duration, we had a 2-week test period to demonstrate that this is going to work in real time, with the real treatment plant, with the real water, all that. The procedure included running the groundwater plant, the treatment plant as before, with a number of the extraction wells online, and we ran it 4 to 8 hours per day. The treatment conditions that were applied included a peroxide dose. We went with 25 milligrams per liter. We were confident that that was going to be a good starting point. We wanted to start low, and then if that wasn't effective, then we could increase it up to, up towards more like 50 milligrams per liter. And again, we decided to start, the pH, instead of going all the way to 3 right off the bat, we decided to go to start with a set point pH of 5. Now that's the pH set point in that first tank. As it turns out, adding the peroxide in the second tank does reduce the pH further, and so that kind of gets you more into the more reliable range to make sure the Fenton's process is in fact working reliably. For the startup phase, we were collecting samples across a number of sampling points every day. We were also checking residual peroxide at various points, because if the peroxide hadn't all been used up, there would be a need to quench that peroxide, and so that was one reason driving a lower starting dose, because that would just mean less potential residual peroxide. This is it's sort of the same diagram, just in a different format of that block flow diagram I had shown you before, just with the sampling points annotated. So our first sampling point, SP number 1, was our influent. So this is the water after it's been commingled from the various extraction wells as it had been previously, but now the water is flowing into the pH adjustment tank of the Fenton's process. And then we had a sampling point between the two. And then post Fenton's, post reaction, we have sampling point number 2, which was already there anyways, but now it has a different implication. From sampling point 2, the water goes, or I'm sorry, the sampling point 3 was after the plate settler. There's actually a splitter box which takes the treated water. So after the splitter box is sampling point 3. So this represents water after the plate settler, before filtration. Then we have sampling point 4 after the filters, sampling point 5 after the air stripper. During startup, I believe we did have that online, and so we just have a sampling point there. Sampling point 6 is after the GAC absorption process. This is our daily sampling schedule. So I'll show the different sampling points. There's different terminology depending on which source you're using, but sampling point 1 2, 3, 4, 5, 6, and then 7 is between the two Fenton's tanks. We did a number of analyses on site, including pH, and we were measuring the residual peroxide, as I'd mentioned. And we also were just looking at metals just as a process control analysis. But we also had commercial analyses for 1,4-dioxane, vinyl chloride to give us our hard performance data. And also we wanted to track metals at a couple locations just to show what was going in and then what was coming out. And then we also looked at TOC as well, just because that was a potential that could potentially place a demand on the peroxide. So what's shown here is that flow diagram with the sampling points annotated with the results. This just shows the results at pH 5.5. So that was one of the tests, one of the test days where the plant was run at pH 5.5 with an influent peroxide dose of 25 milligrams per liter. The influent was similar to what we saw during pilot testing, including a concentration of 1,4-dioxane of about 1.4 micrograms per liter, and the vinyl chloride around 9 micrograms per liter. Post Fenton's, the concentration was actually there were a couple tests where the concentration was above the detection limit of 0.17, but even in those situations, it was generally less than 0.3 micrograms per liter, so still well under the interim groundwater treatment criterion. And vinyl chloride was non-detect. Now, one interesting finding was the GAC, which was a holdover from the the GAC had not been replaced. It was in place, and so when we started back up, we were still working with the GAC that had been in place, and there was actually a detectable dioxane concentration. So that's just the only conclusion there is that even though 1,4-dioxane is not efficiently absorbed to GAC, there is some level of absorption that occurs, and it's likely that there could have been some desorption. And as it turns out, basically that was a normal process. And so with new GAC, we were quite confident that there would be no more dioxane 1,4-dioxane going into the GAC absorbers, and so there would be none to accumulate and potentially desorb. So there was no concern there. And I'll just show a couple of the metals here, including iron. So just like during the pilot test, we showed around a 50 milligram per liter influent concentration, most of which was in the dissolved form. So likely very much most of that was ferrous or Fe+2. And then I'm also showing the arsenic concentration of around 9 coming in. After Fenton's, most of the iron is removed. And actually, the 1360, I have to this is post settling. So there is still some in solution, but it's not like we just took a homogenized sample for the iron here, or else it would have been about the same as the influent. So we were able to show that most of it had settled and the dissolved portion was very small. And so any, following filtration, you would expect a very low iron concentration, and the arsenic was completely removed. So the peroxide was a very suitable alternative for providing the oxidation that was needed to remove the iron and to co-precipitate arsenic. This is just a summary of the results from the various runs. I just show the discharge criteria here for the 1,4-dioxane of 0.4, and also there's a criterion of 1 microgram per liter for vinyl chloride. Every test we ran, the 1,4-dioxane was completely removed to non-detect, as was the vinyl chloride. We even did a test where we didn't do any pH adjustment. The native pH was around 6.4, and even during that test, the effluent 1,4-dioxane and vinyl chloride were reduced to non-detect. Now, this is just a summary of continuous operating data following startup. It's a little dark, I realize, but basically this is showing a period. If you can see this vertical green line here around the end of January, that's around when we went into full scale, resumed full scale. Oops, sorry about that. Full scale operation. The trace, the dark red trace here shows the influent 1,4-dioxane collected every month. The trace down here shows the effluent 1,4-dioxane consistently non-detect, except for one sample where it was around 0.2 micrograms per liter, but still well underneath this 0.4 microgram per liter criterion shown here in the salmon colored trace or line. So the takeaway is that since startup and routine operation, it's been performing as designed and intended to remove dioxane. Just a few observations. As I mentioned, it's reliably achieving 1,4-dioxane removal down to below that interim discharge criterion. An unexpected benefit, I guess you could say, was that there's also been a reduction in sludge generation. I don't have any theories as to why that's the case, but it's an observation. And also another nice thing that has happened is there has been a significant reduction in the frequency of GAC backwashes. It used to be sometimes there would be a backwash required as often as once per day, depending on conditions. Now we're looking more like at a weekly to even less frequent backwash. Again, we don't know the exact reasons. It could be due, there's a couple, you could speculate that maybe a reduction in organics because the Fentons is taken care of. If it's treating the 1,4-dioxane and the vinyl chloride, it may also be reducing other organics that might otherwise have been available from microbial growth in those GAC absorbers. It also could be due to the fact that we changed the polymer. So anyways, long and short is that we are seeing less need for backwashes. Now, there is an increase in the overall chemical use. We did have to add sulfuric acid and hydrogen peroxide, and so there was a cost involved with that. And then we're also increasing the use of sodium hydroxide to readjust the pH following the Fenton's process to get it to discharge criteria and to precipitate the iron. So in conclusion, the Fenton's reaction was successfully integrated into the groundwater treatment plant. It required very few physical um, alterations. Like I had shown you, we removed one process and just put those two tanks in there as a replacement. So physically it fit seamlessly into the existing treatment plant, and it provided a relatively uncomplicated means to address 1,4-dioxane versus having to have a UV or an ozone system, which would have been probably a lot more complicated and expensive. So the benefits, we were able to demonstrate effective treatment without the supplemental iron. And as I mentioned, it's a relatively seamless integration into the existing treatment plant. Definitely cost effective and simpler compared to the other advanced oxidation processes. Also, we're able to avoid bromate generation that sometimes plagues, especially ozone peroxide treatment. As I mentioned, there's reduced sludge generation and reduced GAC backwash frequency. I'd like to make a few acknowledgments. I'd like to thank our client who we've worked with since building the treatment system and then operating it since 2011. I'd also like to thank the industrial water wastewater treatment practice. Matt McGowan has been the project manager for the treatment operations down at the site since 2011. I'd also like to thank Jamie Fettig, who is our manager of the industrial water wastewater treatment practice. A couple of engineers, Kyle King, performed the second phase of the bench scale treatment testing, and Ajish Nambiar managed and led the pilot study. I'd especially like to thank the treatment plant operations team, Mike Carroll and Bill Cliver. A special shout out to Bill, who started the treatment system back up after the prolonged shutdown during the construction of the Fenton's reaction process. Having been there at the time, I was able to see exactly what it took to start a treatment system back up with just basically gremlins in every single PLC and mixer and all kinds of issues, which Bill was able to troubleshoot and resolve so that we could successfully perform and demonstrate startup of the Fenton system and then continue operation thereafter. And I'd also like to thank the technical webinar team, Jessica and Christy, as well as Daniela Savine, who administers the professional development hours certificates. So with that, I'd like to start the Q&A part of this.
Thank you, Ted. That was a great presentation on how you can exploit the existing groundwater chemistry to improve removal of contaminants. A much more sustainable option, like you said, than some alternatives that could have been done. If there's any questions, you can either raise your hand and we can unmute you to ask it live, or you can enter it into the chat. It looks like we already have a few in the chat that we can address. So the first question is from Eleanor Larson. Are there any special considerations for storing and pumping hydrogen peroxide?
It's out in the open. There actually, I don't believe there had to be a special electrical classification, and anybody who's on this who would know better, please, chime in. But the one thing I did want to mention about the peroxide is that we deliberately went with a 30% solution. The reason is that remains below 35%. And so 35% or higher is classified as a quote unquote chemical of interest under the chemical facility anti-terrorism standards. And so keeping it at 30% was certainly a consideration so that we didn't have to, we didn't exceed that threshold. Otherwise, I can't, I don't, I'm not familiar exactly with, there are some specific storage requirements. I think there's some temperature monitoring that's required. Otherwise, we could certainly talk more about that offline.
Okay, the next question is from Emma Sauer. How would you go about determining if Fentons could be a viable option at other sites to address emerging contaminants like 1,4-dioxane?
So obviously the main driver, so what was nice about this plant, or why it worked so well here, is number one, with an existing plant, we also had iron, a lot of background iron, and so that seemed to be a really good fit. Other plants, depending if you have a plant already up and running, it could still be a viable option. You might have to add supplemental ferrous iron. Of course, depending on the situation, like if you're looking at a new system, it may make, that hasn't been built yet. You may want to look at something to the effect of, the UV or ozone peroxide, especially if, depending on whether bromate ends up becoming a concern or not.
Okay, next question is from Jeffrey Snell. Is heat a concern during the reaction?
I don't think so. And I think mainly because the doses have been low enough that really hasn't been much of a concern. I'm trying to think if we ever were monitoring temperature, but it never seemed to, it never had been a concern that we were aware of. And like I said, it certainly hasn't been a concern or an issue during full scale treatment. I mean, one of the nice things is that the groundwater is at a relatively low temperature. It's probably around, I think, 60 Fahrenheit. And so even if it had heated a little bit, it wasn't going to be significant enough that it was going to be a concern.
Okay, so I think because we're at the end of our time, we'll maybe pause there for questions. If anyone else has any questions, feel free to reach out to Ted directly. His contact information is here on the slide. And then we can go to the next. So our next webinar will be on May 9th, presented by Matt Vedder and Kristen Brooks on remediation achievements on the lower Genesee River. It'll be at the same time, 12:30 to 1:30 p.m. Eastern. As I mentioned, a link to the form for PH credit has been posted a few times in the chat, as well as the questions that you'll need to answer on there. If you have any issues getting that and you'd like a PH credit, please let us know and we can help you out with that. And if you missed any questions, you can review it, the webinar, once it's posted on our YouTube channel in the next few days. Thank you to everyone who joined us for today's webinar, and we hope to see you again in May.